In the previous class, we looked at one dimensional flow with heat addition, where we were looking at a flow situation like this. So, let us say this is a duct or a pipe in which heat is added, and at entry the flow is at state 1, and at outlet or exit the flow is at state 2. And starting from the inlet state, which was at P1, let us say T1 U1 and P01 comma T01, we wanted to find out the exit state, which is P2 T2 U2 and P02 comma T02. We would like to do this for two conditions: one, when the inlet flow is subsonic, and another condition when the inlet flow is supersonic. Both situations occur in real life, so we would want to look at this. And our strategy yesterday was to look at the effect of adding an incremental amount of heat, let us say delta Q, which would cause an incremental change in stagnation temperature dT naught. So, we started from this state, we saw where the state would go, or we developed equations that would tell us where the state would be with the addition of an incremental amount of heat, and the idea is to then progressively go and until we reach the exit. That was what we were trying to do, and show the process on a TS and PV diagram. To that end, we had developed the following equations. We wrote down the following equations. I am going to write them down because we will use them very extensively in today's lecture. And if you remember, we wrote everything in terms of changes in stagnation temperature, because that is the effect that we are looking at. This is the change in incremental change in pressure, and now we look at incremental change in temperature, which looks like this. And change in entropy, change in velocity can also be written down, du over u, and change in Mach number finally. So, these were the equations that we had written down. One additional equation that we are yet to write down is the change in stagnation pressure. Remember, the stagnation pressure is P01 here and it is P02 here, and we know that addition of heat increases the entropy. So, we expect P02 to be less than P01. So, that is the other equation that we are going to derive. Let us look and see how we can do this. So, we already have this relationship ds equal to this times dt naught over T naught, and if you remember from our earlier lecture, we showed that the entropy change between two states x and y can be written in terms of the stagnation quantities as Cp times natural log T0y divided by T0x minus or natural log P0y divided by P0x. This we wrote down earlier, and if I take state y to be infinitesimally different from state x, then I can write this entropy change as follows. So, ds is equal to Cp times natural log. So, T0y is infinitesimally different from T0x. So, I am going to write this as T0x plus dT0 divided by T0x minus or natural log P0x plus dP0 divided by P0x. Or if I write this like this, I can write this as Cp times natural log 1 plus dT0 divided by T0x minus or natural log 1 plus dP0 divided by P0x. And I can expand this natural log of 1 plus a small quantity. Remember, dT0 is a small quantity. So 1 plus epsilon, natural log 1 plus epsilon can be expanded in a power series and approximated very well like this. So this is Cp times dT0 divided by T0x minus R times dP0 divided by P0x. Because I can easily replace x with 1 and I have what I want. So basically what we are looking at is the following. So if this is state 1 and I add an incremental amount of heat, that results in an incremental change in stagnation temperature dT0. So ds then is going to be, I can easily replace this and write this as Cp times dT0 divided by T01 minus or dP0 divided by P01. Okay. So now all we do is let me just make a small change here. Let me write this as, instead of 1, let me just write this as without subscript, so that we get a generic relationship relating dP0 and P0 for an incremental addition of heat. So I can now equate this expression for ds with this expression for ds. Right. If I equate these two expressions for ds, I get the following: Cv gamma times 1 plus gamma minus 1 over 2 times m square times dt0 over T0 is equal to Cp times dt0 over T0 minus or times dP0 over P0. If I do a little bit of algebra and rearrange this, this actually works out to be something very simple. Notice that Cv times gamma is nothing but Cp, right? Gamma is Cp over Cv, so Cv times gamma is Cp. So if I do a little bit of algebra, I end up with a very simple expression for dP0 over P0, which I am going to write here along with the other equation. So dP0 over P0 is equal to minus gamma times m square over 2 times dt0 over T0. So now everything is in place. Starting from state 1, I can calculate changes in the quantities that I wanted as I go from 1 to 2. Only thing is, we want to illustrate this on a TS diagram and see how the process goes as I add heat in a duct like this. Okay, let us do that. So what I am going to do next is the following. We are going to look at two situations. So I am going to tabulate So we are going to see what happens when I add heat to a subsonic flow and to a supersonic flow. Similarly, you can see what happens when I remove heat from a subsonic flow and a supersonic flow. Although this is, as I said earlier, this is not of interest to us generally. So I am going to concentrate only on this situation when we add heat to a subsonic flow or a supersonic flow. So this corresponds to heat addition. So Q is positive because the stagnation temperature increases. right. So, this corresponds to heat addition. So, let us look at these quantities one at a time. So, dT0 is positive, right, m is less than 1. So, that means this quantity in the denominator is positive, this is also positive. So, that means the density decreases, right, d rho is negative. So, that means when I add heat to a subsonic flow, the density decreases. Let us look at pressure, positive, this term is positive, this term is also positive, square, this is positive. So, pressure, what happens to the pressure? P decreases, right, dP is negative. So, pressure also decreases if I add heat to a subsonic flow. Is this argument clear? So, we are looking at everything term by term. Yeah.
So, can you repeat again?
Which part do you want me
density.
to? Density part. Okay. So, we are looking at adding heat to a subsonic flow. So, dT naught is positive, correct. This term m is less than 1, the term in the numerator is positive, m is less than 1. So, this is also positive. So, that means this entire thing is positive, there is a negative sign here. So, d rho is negative, that means density decreases, right. We are doing the same thing here, this is positive, this term is also positive for m less than 1, this is also positive for m less than 1, and this is m square, there is no problem. So, dP is also negative, P also decreases. Okay. Next, we are going to look at temperature. Now, temperature is a little bit tricky, this term is positive, correct, this is positive, this is also positive, m is less than 1, but if you look at this expression, this is positive only when m is less than 1 over square root of gamma. Okay. So, generally then when m is less than 1 over square root of gamma, dt is positive. So, I am going to write it like this. So, T increases when m is less than 1 over gamma, right. So, that is very important. So, let me just put a circle around this and then we will write it here. So, for m less than 1, the static temperature increases if m is less than 1 over square root of gamma with the addition of heat. And interestingly enough, the static temperature actually decreases when m lies between with the addition of heat. So, this is a very peculiar region in the flow field where the flow velocity and conditions are such that when I add heat to a flow, subsonic flow at this Mach number, the static temperature actually decreases. Okay. It is not of major significance, it is just of academic interest that there can be a region like this. Okay. So, static temperature, now we have generally the static temperature increases, we have written that over there. Now, we go to entropy, this is positive, this term is also positive. So, entropy in this case increases, and let us go to Mach number. Instead of velocity we will directly go to Mach number. So, Mach number also if you see positive, m less than 1, this is positive, this is also positive. So, Mach number increases in a flow like this. So, m goes up. And what about stagnation pressure? This is positive, right, this is positive. So, that means stagnation pressure, this is negative. So, stagnation pressure decreases in this case. So, P naught decreases. Now, just for the sake of completeness, we will write down that T naught is actually increasing, which is over there, it is redundant. So, that is for a subsonic flow. So, for a supersonic flow, if you try to do the same thing, m is greater than 1. So, that means this is positive, this becomes negative because m is greater than 1, there is a negative sign here. So, that means d rho is positive, right. So, rho increases. And if I look at pressure, same thing, positive, this term is positive, this is negative, which counteracts this negative sign. So, dP is positive, so that means P increases. Static temperature, again positive, negative. Now, if you look at this term, when m is greater than 1, this term is always negative. When m is greater than 1, this term is always negative, this is negative, so that counteracts each other. So, temperature will increase, dT is positive in this case also, right. So, I can write T is positive in this case also for any supersonic Mach number, and then we look at entropy, again positive, this term is always positive, so S increases in this case also, right. S increases, and Mach number, if I see this is positive, M is greater than 1, so that means this is negative, I am sorry, I should be looking at this is positive, M is greater than 1, so this is negative, this term is positive, so we end up with dm decreases because this term is negative, right. This is positive, this is negative, this is positive, so dm is negative, so that means the Mach number decreases. And P naught, again positive, this is positive but there is a negative sign in front, so stagnation pressure decreases in this case also. And just for the sake of completeness, we will say T0 increases. So, if I summarize what we have said here, heat addition to a subsonic flow increases the Mach number. So, if the fluid enters the duct let us say at Mach number 0.4, then when it leaves the Mach number is going to be 0.5, 0.6 depending upon how much heat we add and the mass flow rate. This is all for a fixed mass flow rate. So, the Mach number increases, static temperature increases but static pressure actually decreases with the addition of heat for a subsonic flow. If it is a supersonic flow, then the Mach number decreases. Let us say we have the flow coming in at a Mach number 2.5, as a result of heat addition it may go to 2 or 1.5, right, and the temperature increases, pressure also increases. There is a loss of stagnation pressure for both cases and entropy increases in both cases. That remains the same whether it is subsonic or supersonic. The increase in entropy here, you must remember that the increase in entropy here is not due to entropy generation. Remember we said that entropy change is due to entropy transfer plus entropy generation. Here there are no irreversibilities, so there is no entropy generation. So, the increase in entropy is solely due to transfer of entropy, because we are transferring heat, we are also transferring entropy to the system. This can be a reversible heating process, but still the entropy will increase because we are transferring entropy to the system. So, that is what this is due to, which is why entropy increases in both the cases, subsonic and supersonic case, and stagnation pressure decreases in both the cases. Okay? That is a summary of the findings. What we want to do next is, starting from the inlet state, I want to sketch the process that the fluid goes through. For each delta Q addition, I want to know where the next state point is, then I want to keep track of, I want to draw the locus of all such state points so that we go from inlet to outlet. Okay? This we are going to do on a TS diagram and a PV diagram. That is what we are going to do next. So, just like what we did before, we are going to combine this equation dt over T and this equation for ds to get the following. Let us combine. So, if I combine the equation for dt and ds, we get the following: dt over ds is equal to 1 minus gamma m square over gamma times 1 minus m square times P over Cv. So, this is the equation that describes how the state is going to change, right. Remember, we use this type of equation to draw isobars, isotherms and isentrops and so on. We are going to use the same strategy to draw a line like this. This line on a TS diagram is known as a Rayleigh line. So, when we complete drawing this line, this is known as a Rayleigh line. Okay. Now, you will also remember from our earlier lecture that the slope for a P equal to constant line, the slope for a P equal to constant line on a TS diagram was given as T over Cp. You must recall that. So this allows me to compare these two, and we can then sketch the diagram as follows. So first let us write down some salient points that we have from these equations before we before we draw the TS diagram. What are the salient points from this? Let us see. If m is greater than 1, let me do that first. So if the flow is supersonic, then m is greater than 1, m is greater than 1, so the term in the denominator is negative, term in the numerator is also negative, but dt ds is positive, right, the slope is positive. For m greater than 1, and if m is greater than 1, then comparison of these two equations tells me that the Rayleigh line at any point is steeper than the isobar which passes through the same point. Okay, so I can write that next. Rayleigh line is steeper. Steeper than the isobar. Now as m tends to 1, remember we said that when you add heat to a supersonic flow, the Mach number decreases, right. So you start from Mach number greater than 1, it keeps decreasing, and as m approaches 1, right, notice that dt ds approaches plus infinity, right, because dt ds is always positive, and as m approaches 1, dt ds approaches plus infinity, right. So as m goes to 1, dt ds approaches plus infinity. So I get an idea of what this line is going to look like now, at least the supersonic branch of the line, I know what it is going to look like, right. So that is what we are going to look at, see in the diagram. So if you look at the diagram, right, so we are starting with state 1. Remember this is a supersonic state, which is why it is over down here, and notice that the isobar is less steep than the Rayleigh line. So the Rayleigh line is shown here using a thick black line, as you can see from here, and the isobar, which is this one here, is less steep than the Rayleigh line, and this is the supersonic branch. So we keep moving like this, the slope is positive as we said earlier, right, and it is steeper than the isobar. So we keep moving like this, and as we approach m equal to 1, notice that the slope becomes the slope approaches plus infinity. So the slope is initially positive, and then as I keep going like this, it is not really a straight line because the slope, as you can see from here, keeps changing with temperature and Mach number. Okay, so it's actually curved, and as we approach m equal to 1, this approaches plus infinity. The slope becomes plus infinity. That is what is shown in this diagram, right. When it approaches m equal to 1, you get plus infinity. Okay. Now we are going to look at the subsonic portion of the curve. So let us see what that looks like. So we can draw similar kind of inferences on the subsonic portion of the curve from here, right. For when the flow is subsonic, this is positive, and if m is less than 1 over square root of gamma, this is also positive, otherwise it is negative, right. So, let us write it down. Slope is positive if the Mach number is less than 1 over square root of gamma, and the slope is negative if the Mach number lies between 1 over square root of gamma and 1. Okay. And it is also easy to show that when m is less than 1 over square root of gamma, it is quite easy to show by comparing these two, that if m is less than 1, the Rayleigh line is actually less steep than the isobar. So, Rayleigh, in this case, in the previous case it was steeper. So, in the subsonic case the Rayleigh line is less steep than the isobars. And as m approaches 1, right, remember once m becomes larger than 1 over square root of gamma, the slope becomes negative. So, as m approaches 1, the slope approaches from the negative side. So, dt ds is approaches minus infinity, right. So, dt ds approaches minus infinity. So, as m approaches 1, dt ds minus infinity. So, if I summarize this, for certain values of m less than 1 over square root of gamma, the slope is positive, and as it keeps increasing, I get to a value 1 over square root of gamma. Beyond that, the slope becomes negative, which means it goes like this, and then as I approach m equal to 1, it comes like this, minus infinity, right. That is what those are the inferences that we get from this equation, single equation, right. We are now going to transfer it to the TS diagram. So, to summarize what we said earlier, state point 1, if it is supersonic, it lies here. The Rayleigh line is steeper than the isobar which passes through this, and the slope approaches plus infinity as we approach m equal to 1. Subsonic state lies above like this, and the Rayleigh line is less steep than the isobar. Here is the isobar corresponding to p equal to p1. The Rayleigh line is less steep than that, and the slope keeps increasing. Once I reach m equal to 1 over square root of gamma, the slope will then become negative. So, I can see the curve turning downwards like this, and as I approach m equal to 1, we approach dt ds equal to minus infinity. Okay. I am not going to make an effort to show that these two curves actually join at the same point, but it is not very difficult to show that. Okay. It is also possible that you get one curve which goes like this, another one which comes from above and then goes like this, but that does not really happen, they actually merge. Okay. I am not going to try to demonstrate that in this case, and you can see, for example, that the stagnation pressure in both cases will decrease because the isobars, if you remember, diverge from each other. So, the stagnation pressure P01 is going to be greater than the stagnation pressure P02. Okay. So, most of the inferences that we have drawn here and in the table are now available here. So, you see that P2, for example, in the supersonic case, because of the slope, P2 is greater than P1, whereas in the subsonic case, notice that P2 is less than P1, right, because the Rayleigh line is less steep than the isobar here. P2 is going to be less than P1 for the subsonic case, whereas P2 is going to be greater than P1 for the supersonic case. In both cases, T2 is greater than T1, right. So, the diagram actually captures all the information that we have put down here. So, if you remember, for a subsonic we said static pressure decreases, static temperature increases, that you see from here, right, and for a supersonic flow, static pressure increases, static temperature increases, that also you are able to see from this diagram. So, the diagram captures the essence of what we have done so far. So, there are two branches to the Rayleigh line. one is the subsonic branch, other one is the supersonic branch. Okay. Our next task is to draw the same diagram on a PV coordinate space. Right. Now before we do that, we want to before we close this, there is one important point that I wanted to demonstrate, namely heat addition to a compressible versus an incompressible flow. Remember earlier we said that addition of heat to an incompressible flow does not cause a change in pressure. Now we are in a position to actually examine that mathematically and see if it is indeed true or not. That is what we are going to do next. Okay. So we are now going to look at the incompressible limit If you recall, we had defined the speed of sound A as the square root of Tp d rho for an isentropic process, right. If the fluid is incompressible, by definition, irrespective of the pressure change, the density remains the same. So I can have whatever delta P I want, but delta rho is essentially 0 or very small. There is no change in the density of the fluid. So the speed of sound for an incompressible fluid by definition is going to be infinity, very large, right, very large, or in the incompressible limit A tends to infinity or very large values. Just for as an example, speed of sound in air under normal atmospheric condition is about 330 meter per second. Speed of sound in water under similar condition is nearly 1.2 kilometer per second. So it becomes very large. Okay, so underwater explosions are much more powerful, mainly for that reason. Okay, so in the incompressible limit, the speed of sound approaches infinity, which means that the Mach number, what is the Mach number going to do? So irrespective of u, right, Mach number is u over a. Irrespective of u, the Mach number is going to approach 0. So that is the incompressible limit, and that is what we are going to do in these equations. We are going to see how these equations behave when we allow the Mach number to go to 0, right. So let us look at the first equation, density. So in the incompressible limit, how does the density behave for heat addition? So dT naught is positive, m approaches 0 in both these cases, so the numerator becomes equal to 1, denominator also becomes equal to 1. So d rho over rho is minus dt naught over T naught. Next, P, dP over P, dt naught is positive. This quantity, as m goes to 0, this goes to 1, this also goes to 1, but notice that this goes to 0. So dP tends to 0 as m goes to 0. And what about dt over T? dt over T is given over here. This term goes to 0, I am sorry, this term goes to 1, this term also goes to 1, and this term also goes to 1. So dt over T is dt naught over T naught. So you see mathematically that for an incompressible fluid, addition of heat, dt naught is positive, addition of heat does not cause a change in pressure. right, which was why, if you remember, we drew the temperature variation along the length of the gas turbine engine or the aircraft gas turbine engine, and you remember that in the combustor the pressure remained more or less constant. This tells you why the pressure remains more or less constant. The flow behaves like an incompressible fluid in the aviation gas turbine combustor. Okay. So, this actually can be used as a check for incompressibility. If I add heat and I do not notice change in pressure, that means compressibility effects are negligible, right. So, you have huge furnaces where you are adding a lot of heat, but compressibility effects are negligible. This is the reason for that. And you also notice that if the flow is compressible and I add heat to the flow, then definitely there is going to be a change in pressure. Our TS diagram showed that, and we also know from this equation that the pressure is going to change, either increase in a supersonic situation or decrease in a subsonic situation. Okay. So, this proves very clearly that what we said in our first lecture regarding compressibility can be proven mathematically also from the proper equations. Okay. Our next job is to transfer the information to a PV diagram in PV coordinates. That is what we are going to do next. So, we start with the PV diagram of Rayleigh flow, and if you recall, when we illustrated the normal shock solution on a PV diagram, we rewrote the equation slightly before doing that. So, if you remember, the continuity equation in this case is rho 1 u1 equal to rho 2 u2 equal to m dot over A, and we defined this to be the quantity G. Right. That is what we did, and the momentum equation was the same. So, P2 plus rho 2 u2 square is equal to P1 plus rho 1 u1 square, from which we derived the Rayleigh equation, which was P2 minus P1 divided by V2 minus V1 equal to minus G square. Right. This was what we had written down. So, this is the Rayleigh equation in PV coordinates. Notice that this is a straight line in PV coordinates. Right. This is the Rayleigh equation in PV coordinates. It is the same whether we are looking at a normal shock solution or flow with heat addition, because the governing equations have not changed up to this point. So, this straight line in PV coordinate is the same as this Rayleigh line that we have just illustrated. Right. This is the Rayleigh line in TS coordinates. Okay. So, the same Rayleigh line in PV diagram is a straight line. Remember, this Rayleigh line that we have sketched here is also for a fixed value of mass flow rate, and this is also for a fixed value of mass flow rate. Okay. So, if I transfer this information to a PV diagram, let us say this is my state 1. since the slope of the Rayleigh line is negative, as we argued earlier, as the slope of the Rayleigh line is negative, states in this quadrant and this quadrant are not allowed. So, I can either have a Rayleigh line which looks like this, or I am allowed to have a Rayleigh line which looks like this. In the previous case, normal shock solution, we said that any state here would have a lower value of entropy and hence is not allowed. We need to see whether that is true in this case also. We do not know. So, we will say that states in this quadrant and states in this quadrant are allowed. For now, we will say that when we look at H equation also, remember state 2 must lie at the point of intersection of the Rayleigh line and the H equation. So, at that time we will decide whether downstream states here are allowed or not. Okay. For now, we will let this be. Notice that this is a straight line, the slope is minus g squared. This, now we have to determine which one is the subsonic branch and which one is the supersonic branch, because if you recall the TS diagram that we had here, this was the subsonic branch of the Rayleigh line, this is the supersonic branch of the Rayleigh line. The same Rayleigh line is being drawn here, so we need to determine which is the subsonic branch and which is the supersonic branch. In order to do that, we make use of the information that we already put down. If you remember, for m less than 1, right, with heat addition, right, with heat addition, meaning if T0 increases, then we said that rho, what did we say about rho? We said that rho decreases, correct, rho decreases, P decreases and T increases for a subsonic flow, and for a supersonic flow, if you add heat, then we said that rho increases, P increases and T increases. Right. So, we can use this information to determine which is the subsonic branch and which is the supersonic branch. Right. So, if for example, let us say state 2 lies here, then the pressure has increased. What about the, since we are using specific volume, what about the specific volume? Specific volume has actually decreased in going from here to there. So, that means density has increased, right? Specific volume has decreased, density has increased. What about temperature? If you remember the shape of the isotherms that we drew, you will know that the temperature here is higher than this. So, that means the stagnation temperature has increased, we have added heat, pressure has increased, right, specific volume has decreased which corresponds to this, and static temperature has increased. So, that means this is the supersonic branch of the Rayleigh line, right, that is the supersonic branch of the Rayleigh line. Is that clear? Excuse me? I am sorry, thank you, m greater than 1, thank you. Yeah. Is that argument clear? Should I repeat it? Is it clear? Okay. So, similarly here, if state 2 were to lie, let us say somewhere here, then obviously pressure has decreased, right, specific volume has increased, which means density has decreased, and static temperature has, in some cases, in this case if it's so far down, static temperature could have actually decreased. That depends upon the shape of the isotherms. In general, the static temperature would increase, right, depending upon the shape of the isotherm. So, this corresponds to the subsonic portion of the Rayleigh line. Okay. So, this corresponds to the subsonic portion of the Rayleigh line. Okay. And remember, the Mach number decreases as I travel outwards from here, and the Mach number increases as I travel outwards from here. Okay, for a given stagnation temperature, Mach number increases in this direction and Mach number decreases in the supersonic portion of the Rayleigh line. So, you must remember that, because when we will need all this information when we transfer the information from our equations to the diagram. Okay. The next thing to do is to draw the H line corresponding to flow with heat addition. Once we do that, we can combine the two and come up with the information on a PV diagram, which we will do in the next class.